Hello everyone. The title of this presentation is Turning Strengths into Weakness, a certified robustness-inspired tech framework against graph neural networks. First, let's quickly preview our work. In this paper, we study a problem, that is, can the existing graph invasion and poisoning attacks to GNNs be further improved? The answer is yes. Specifically, in this paper, we propose a certified robustness-inspired attack framework to GNNs. It is worth noting that we are the first work to use certified robustness for attack purpose. Then we conduct an extensive experiment to demonstrate the effectiveness of our attack method. Here, we provide a motivating example. In this page, I will present our work from the following parts. The first part is motivation. The second part is preliminaries. And the third part is our attack method. The fourth part is evaluation. In the final, we will give a conclusion. As we know, GNNs are vulnerable to adverse attacks both in test phase and training phase, and there are a lot of existing attacks. Can we design a general attack framework that can further enhance both the existing graph invasion and poisoning attacks to GNNs? The answer is yes. In this paper, we focus on attacking GNNs for node classification task, where we have a graph with node set V and edge set E. We use A to denote the adjacency matrix. To perform node classification task, we have to train a node classification f theta on training nodes VTR. In order to learn f theta, different GNN algorithms like GCN, SGC, GAT minimize a loss function L. By contrast, we focus on structural attack where graph perturbation matrix delta can be defined in a binary space. A plus delta is a perturbed graph. In this slide, we present graph evasion attacks to for a trained node classify f theta to misclassify as many testing nodes as possible on the perturbation budget capital theta. Please refer to paper for graph poisoning attacks. The existing graph invasion attack is to maximize 0 to 1 attack loss using optimal perturbation delta on the budget. However, it is challenging to solve because the indicator function is hard to be optimized. Therefore, it is usual to use an alternative optimization problem where the per sample loss is used to optimize the indicator function. Can we improve the graph invasion attack efficiently? Yes. We will leverage simplified radius to achieve this goal. Now, we present our idea to improve the existing attack. Simplified robustness was originally used by defenders to guarantee the robustness of classification model. As seen in the figure, node 2 has a large CR and is more robust to adverse perturbation. Other nodes have relatively small CR and are vulnerable to adverse perturbation. Therefore, we have observation 1. A node with a larger simplified perturbation size should be disrupted with a smaller number of perturbed edges, and vice versa. According to reference 1 in KDD, we can calculate simplified perturbation size of each node. With simplified perturbation size of each node, we can perform a more effective attack by sorting our nodes' simplified perturbation size in an ascending order and perturbing the edges of the sorted nodes one by one. However, this solution is both computationally intensive and suboptimal. Therefore, we design a simplified perturbation size inspired loss that assists to automatically seeking the ideal edges. To this end, we have defined a node's weight that is inversely proportional to simplified perturbation size. Then we have observation 2. A node with a larger simplified perturbation size is assigned a smaller weight, and vice versa. Thus, we have weight design equation. With simplified perturbation size inspired loss, we can incorporate it to the existing attack methods, that is to directly optimize our designed loss. For example, combining PGD in graph invasion attack, we can obtain simplified robustness inspired PGD. We provide a motivating example in the slide where our budget is to perturb two edges. As we can see, the nodes with smallest CR will be considered to be perturbed. Next, we present experiments. We consider GCN model. The datasets include Coral, SetSeer, and block catalogs. The dataset statistics can be seen in Table 3. The base attack method is PGD with CE loss and CW loss. The performance metric is attack accuracy on testing nodes. Please see paper for graph poisoning attacks experiments. The first experiment is about the overall attack performance. As we can observe, when taking GCN on Coral and the perturbation ratio is 20%, our attacks have a 7% and 5.6% gains. Therefore, our CR-inspired attack enhanced the base attack. The second experiment is about impact of distribution of the perturbed edges on nodes CR. As we can observe, first, a majority number of the perturbed edges connect with nodes with smaller CR in our attack. Second, a significant number of the perturbed edges in basis attack connect with nodes with larger CR. Third, a perturbed edge affects its connected node the most. Finally, let's conclude the presentation. We are the first work to use simplified robustness for attack purpose to GNNs. Second, we extend the randomized smoothing and obtain new CR for graph nodes. Third, we propose a novel simplified robustness inspired node weights.